Good evening, everyone. So, hope you're all staying safe and had a pleasant holidays. We're starting the new semester and we'll be covering in this course the thermal physics, the basic part, which is the part one of the thermal physics. You have more advanced courses on thermal physics in semester five. So, I'll start with the introduction and the basic concepts in the first lecture. Then we'll try to get into more mathematical models and try to understand in depth about the part we need to understand in the thermal physics. So, so this is the structure of the course, which starts with the definitely the kinetic theory of gases, and so the basics are more towards you have to understand the basic assumptions which is the key for the kinetic theory. So in simple, if you want to understand that the gas molecules are always moving, and that is how, or that actually gives you an idea about the kinetic theory. And this is actually approximated. So that's actually linked with the thermal physics, and it's basically the ideal gas approximation that makes it easier to understand. And you'll be knowing about the perfect gas laws, Maxwell distribution laws, root mean square, and most probable speed, which some of the terms you might have come across during your higher secondary courses these days. Now, we'll be knowing about the like the effect of the size of the molecules, the collision probabilities, distribution of free paths, mean free path, Maxwell's distributions, degree of freedom, equilibrium, equipartition of energy, and all that, which are all very interesting topics. I'll not be covering on that. Then the next part is the transportation phenomena like viscosity and thermal conduction, diffusion in gases, further the Brownian motion, its applications. Then, because the first part more deals with the ideal and perfect gases, so you'll be knowing more about real gases afterwards, where we are dealing with the intermolecular interactions. The first part, we are not thinking about the intermolecular interaction, which is available in the physical world. Then we also need to deal with the isothermals of the real gases, van der Waals equations, other equations of like states like and critical constant of gas, law of corresponding states, and real coefficients, boil temperature, and all that. The reason I'm just citing all this because I'll not be covering this part. I'll go more into further down to the conduction of heat and radiation. Now, you need to have some understanding about the first few things, but I think you more or less have the basic, and I'll continue with the understanding about the conduction of heat, where we need to understand about thermal conductivity, diffusivity, Fourier equation for heat conduction. So basically, it's a mathematical model how we can understand the heat conduction, and also the application of this Fourier transformation in various frame of references like spherical or cylindrical kind of structures for the flow of heat. Then further, we'll be knowing about radiation, which is spectral, emissive, and absorption powers, Kirchhoff's laws, black body radiation, energy density, radiation pressures, Stephen's Boltzmann laws, and Newton's law of cooling, Planck's law, and Rayleigh's formula, Wien's law, which should be quite an introduction, like interesting area of study. Now, This first lecture is more dedicated towards understanding how thermodynamics and heat transfer are related to each other, distinguish thermal energy from other forms of energy, and heat transfer from other forms of energy transfers, the general energy balances as well as the surface energy balances we will understand in this course, in this lecture. Understand the basic mechanism of heat transfer, which are conduction, convection, and radiation. Then Fourier's law of heat conduction, Newton's law of cooling, which is not in your course, Stefan Boltzmann law of radiation. So only the basic introduction I'll be like giving you an introduction in this course, this lecture. Identifying the mechanisms of the heat transfer that occurs simultaneously in practice, may not be in your course. Develop an awareness about the cost associated with heat losses. It's something that physically you need to understand, and we can solve a few problems which are encountered in day-to-day practices. Now, the thermodynamics and heat transfer. This course is not named as thermodynamics, so still you'll be understanding the like those parts in the basics of thermodynamics in semester 5, but we need to understand about heat here. So it's basically a form of energy that can be transferred from one energy to another as a result of temperature difference. So when we're dealing with a temperature difference, we're dealing with heat. And thermodynamics is concerned with the amount of heat transfer as a system undergoes a process from one equilibrium state to another. Now, heat transfer deals with the determination of rates of such energy transfer as well as variation of the temperature. It, the transfer of energy as heat is always from the higher temperature medium to the lower temperature one that you already know. The heat transfer stops when the two medium reach to same temperature. It can be transferred in three different modes: conduction, convection, and radiation. So one simple examination, like example would be the thermal flux, what we call, which is generally which has a layer of insulation around your hot coffee. So the insulation actually helps in holding the temperature. Otherwise, if you don't have the insulation, what happens is it starts cooling off very soon. Now, other areas of the heat transfer would be like human body. So our temperature is 37 degrees centimeter, if I remember it correct. And now at a situation where we are talking about post-COVID world, then we have to be very careful about the temperature of the people around us, because somebody can have a fever, which may be an indication. Whereas the air conditioning systems and heating systems also use heavily these heat transfer theories and mechanisms. Electronic equipments, that is something I have worked very much in my research, and a lot of reasons for the electronic systems equipments fail is because unnecessary or unwanted heating. Your laptop may fail if you work with it, like keep it on for several hours. And power plants. So power plants also fail. Sometimes they like fail massively. And refrigeration center, I mean, as you know. Now, we can get into some historical background of all this, which is basically the kinetic theory, which treats molecules as tiny balls that are in motion and thus possess kinetic energy. Now, heat is the energy associated with the random motion of the atoms and molecules. Now, caloric theory, which is quite obsolete now, it says that the heat is a fluid-like substance called caloric that is massless, calorieless, odorless, and tasteless substance that can be poured from one body into another. So that remained like that for quite some time. Then it was eventually thrown out of concept and by several careful experiments by James Joule. So James Prescott Joule is a British physicist, and we know about him much because of his work on conversion of electrical and mechanical engineering into heat and the first law of thermodynamics. So the energy unit Joule is also named after him. The Joule's law of electric heating actually says that he formulated states that the rate of heat production in a conducting wire is proportional to the product of the resistance of the wire and the square, which is the electric current, which is I square R. And through his experiment, he demonstrated, among several things, like mechanical equivalence of heat, that is conversion of mechanical energy into an equivalent amount of thermal energy. That actually built the foundation of the conversion principle. And like he later worked with William Thomson and Lord Kelvin, discovered the temperature drop of a substance during free expansion phenomena known as Joule-Thomson effect. Most of these things you will be learning in this course as we advance. So that actually gives a foundation of operations for the common vapor compression refrigerator and air conditioning system. Basically use this Joule-Thomson effect. Now, while we deal with these kind of equipments, the engineering heat transfer actually needs a few parameters like rating and sizing. When we're dealing with like heat exchangers, boilers, condenser, radiators, heaters, furnaces, and refrigerators, solar collectors, then the rating problem actually deals with the determination of the heat transfer rate for existing system at a specific temperature difference. Whereas the sizing problem deals with the determination of the size of the system in order to transfer heat at a specific rate for a specific temperature difference. Now, an engineer needs to design these devices or equipment, and he needs information from experimental as well as he can do it analytically. So the experimental approach is more towards actual physical system and like measurable quantities. And definitely there'll be experimental error. It's definitely more time consuming and expensive. An analytical approach, which these days we call the modeling, is more a numerical approach. We have more very efficient models that can actually predict what you will be expecting from the experimental results with some error because of our boundary conditions are not always correct. Now, if you think about modeling, then definitely you need to have a detailed understanding about all the equations that are and the parameters that are involved in that physical process. Then you have to understand the physical problem, identify important variables, make reasonable approximations and assumptions, know the relevant physical laws. Eventually, it all boils down into one differential equation. Then we have to apply some solution techniques. So there are several differential equation solution techniques you will be learning in the mathematical physics. And you have to learn how to carefully choose the boundary conditions. Then eventually we get some solution. Now, heat and other forms of energy if you think, then energy can actually exist in numerous forms like the thermal, mechanical, kinetic, potential, electrical, magnetic, chemical, and nuclear. Now, all of these things is basically the total energy. Now, sum of all the microscopic forms of the energy is basically the internal energy. Now, what is thermal energy and how thermal energy is different from heat? So when we deal with internal energy, it may be viewed as the sum of the kinetic and the potential energy of the molecules, whereas sensible heat is the kinetic energy of the molecules. Latent heat is the internal energy associated with the phase of the system. Chemical or bond energy is the internal energy associated with the atomic bonds in the molecule. Nuclear energy is the internal energy associated with the bonds within the nucleus of the atom itself. So there is this term internal energy, another term enthalpy. We'll deal with these things in a more advanced course, just as an introduction in the analysis of the systems, like when we dealt with the fluid flow, then we encountered with this combination of properties, U, which is the internal energy, and the PV. So a combination of these two is the enthalpy, whereas the PV is the flow energy. Now, this one is rather more important at this course, which is the specific heat of gases, liquids, and solids. So the definition of specific heat is the energy required to raise the temperature of unit mass of a substance by 1 degree. And it basically can be done in two ways. At a constant volume, so the specific heat can be at constant volume, and it can be done at constant pressure. The specific heat of a substance in general depends on two independent properties, like temperature and pressure. That is why you have two specific type of specific heats, and we'll know about the relationship between them. At low pressure, all real gases approach ideal gas behavior, and therefore their specific heat depends on temperature only. Now, so the change of internal energy can be very easily predicted, or the enthalpy can be predicted from this one, the specific heat. And much of these things we'll be dealing in a different course. But now we need to focus more into energy transfer. So the energy can be transferred to and from a given mass by two mechanisms, heat transfer and work. The heat transfer rate is basically the amount of heat transfer per unit time, and heat flux is the rate of heat transfer per unit area normal to the direction of the heat transfer. Whereas the power is the work done per unit time. Now, first law of thermodynamics is not here. You don't have to learn it now. It's just for your concept. It basically says it's it's a different version of the conversion of energy principle that states that energy can neither be created or destroyed during a process. It can only change form. So the net change, increase or decrease in a total energy of a system during a process is equal to the difference between the total energy entering and the total energy leaving the system during the process. So that's basically the energy balance for any system undergoing any process in rate form. So in case of a steady state condition, this rate form can be written in terms of rate of net energy transfer in by heat, work, and mass equal to the rate of net energy transfer out by heat, work, or mass. So this applies to all of them. In heat transfer problem, it is convenient to write the heat balance and to treat the conversion of nuclear, chemical, mechanical, and electrical energies into thermal energy at heat generation. So basically, you are considering the net heat transfer with the heat generation as the change in thermal energy of the system. More about the energy balance for a closed system, like something which has a fixed mass. We'll be knowing more about the systems later. The total energy for most systems encountered in practice consists of internal energy U. Now, it is especially the case of the stationary system since they don't involve any change in the velocity or elevation during a process. So a stationary or closed system will actually give you an equation like this. And if you don't have any work, then basically that's the Q gives you equation like this. Which is equivalent to something like a control volume kind of a, or control mass kind of a system where the term steady means no change with time at a specific location. The surface energy balance basically is interesting because the surface contains no volume or mass, and it definitely cannot contain net energy, that is why. And therefore, a surface can be viewed as a fictitious system whose energy content remains constant during a process. So the energy that goes in the surface needs to be also going out with this. So it's valid for both steady state and transient condition. Now, heat transfer mechanism is interesting because that's what we're going to deal here, largely conduction and radiation. Heat as a form of energy can be transferred from one system to another as a result of temperature difference. So in simple, you only have heat transfer when there is a temperature difference. A thermodynamic analysis is concerned with the amount of heat transfer as a system undergoes a process from one equilibrium state to another. The science that deals with this determination of the rates of such energy transfer is heat transfer. So when you're having a heat transfer, all the analysis will be dealing is basically this mathematical concept of heat transfer. Now, the transfer of energy as heat is always from the higher temperature medium to the lower temperature ones, and the heat transfer stops when the two mediums reach to the same temperature. And the processes are conduction, convection, and radiation depending on the medium we're dealing with. All modes of heat transfer require the existence of temperature difference. The part we have in the syllabus now is basically conduction. And conduction is the transfer of energy from the more energetic particle of substance to the adjacent, less energetic ones as a result of interaction between the particles. In gases and liquids, the conduction is due to the collision and diffusion of molecules during the random motion. In solids, it is due to the combination of vibrations of the molecules in a lattice and an energy transport by free electrons. So I'll emphasize again that conduction is basically sort of a result of interaction between the particles. The particles need to interact. The rate of the heat conduction through a plane layer is proportional to the temperature difference across the layer and the heat transfer area, but it is inversely proportional to the thickness of the layer. So in mathematical form, the rate of conduction is basically proportional to the area. So if you increase the area, the rate of heat conduction will increase. So if your surface area increases, naturally you will have more heating or more cooling depending on what we're dealing with. And definitely it's proportional to the temperature difference. So if you have more temperature difference, then it's likely have a faster rate of heat conduction. Now, it's inversely proportional to the thickness, which is also obvious. You can understand by general understanding, like if you have a thicker insulator, then it will release the temperature slowly. It will change the temperature to normal temperature in both sides in a slower manner. Now, it can be mentioned in terms of Fourier's law of heat conduction, which is given by the rate of change of heat, the conduction heat, which is proportional, negatively proportional to the area, and the gradient of temperature in terms of the thickness, which is the x. Here, the K is the thermal conductivity, a measure of the ability of a material to conduct heat. The temperature gradient, which is dT by dx, is the slope of the temperature curve on a Tx diagram. The heat is conducted in the direction of the decreasing temperature. So where the temperature is lower, the heat is going towards that. And the temperature gradient becomes negative when the temperature decreases with increasing x. The negative sign in the equation ensures that the heat transfer in the positive x direction is a positive quantity. We'll be dealing with Fourier's equation here. Now it's good to know about him. He's basically a French mathematician and physicist born in France. And best known for his infinite series. You must be dealing with Fourier series in your mathematical course also. Trigonometric functions bear his name and the development of the mathematical theory of heat conduction. He also developed the partial differential equations governing heat diffusion. He solved using Fourier series, the Fourier transformation, Fourier number, and the Fourier law of heat conduction are named in his honor. Fourier is also credited with the discovery of the phenomena of the greenhouse effect. Now, we all know about that. Thermal conductivity basically is the rate of heat transfer through a unit thickness of the material per unit area, per unit temperature difference. So that basically comes from the equation we just dealt with. So if you consider this diagram, then basically the thermal conductivity, which is the K, we can find out by this equation, which is basically used in experimental measurements. The thermal conductivity of a material is a measure of the ability of the material to conduct heat. So if you have a higher thermal conductivity, it is expected that the material is good heat conductor, and a low value of the uh, thermal conductivity actually indicates that it's a poor conductor or insulator. So definitely it is expected that metals will have a higher thermal conductivity, and that is how the prices or the utility of metals are also defined. So now we know about two kinds of conductivity. One is electrical and thermal. So this one gives you an idea about the range of the thermal conductivity of various materials at room temperature. Let's take a moment to look at all this. So it's obvious that the thermal conductivity for non-metallic crystals like diamond and graphite is outstanding. Even diamonds are used as heat spreaders. This is even superior than silver or copper and iron. But definitely diamonds are expensive. So the price factor also comes in play when we think about the heat spreaders that we use in laptops and other things. Definitely, it needs to be more conducive towards the manufacturing technology that we are using. So metal is definitely conducive for electronic manufacturing. That is why the electronic like fins for heat spreading and all that are generally used with metal, but we definitely try to make it by cheaper metals like aluminum than silver or other things. Now, gases seem to have a quite bad conductivity. The thermal conductivities of gases such as air vary by a factor of 10 power 4 from those of pure metals such as copper. The pure crystals and metals have the highest thermal conductivities, and gases and insulating materials are the lowest. So the thermal conductivity of an alloy is usually much lower than the thermal conductivity of either the metal of which this is composed of. That's an interesting observation. Now, the mechanism of heat transfer is quite different for different substances. While for gas, the forces that actually work in play are the molecular collisions, molecular diffusion that actually carry the heat. For liquid, molecular collision and molecular diffusion. Whereas for solids is the lattice vibrations. So when because because in solid all these molecules are quite strongly bonded and they almost cannot move, which is possible for liquid and gases. So when you see a gas, it's actually all the molecules are moving randomly all across, and you'll be knowing about these things in the kinetic theory of gases. When we deal with liquids, the case is almost similar, but there is still the forces are quite stronger than that. But in all these cases, these molecules can physically move, and that is how they carry the energy. And that is why when we use a boiler to heat, like if you make a cup of tea, then you will see that the water is seems to be like coming from the bottom to the top because the bottom is actually heating up and the light molecules, more energetic molecules are actually coming to the top surface. Whereas for solids, it's not possible for the molecules to move when they're heated, but they can vibrate because they have extra energy. Now, with this lattice vibration, they actually carry the heat from one to another. Also, the flow of electrons do play this. Now, the thermal conductivities of metals also show some interesting property. which is it vary with temperature. The variation of thermal conductivity of various solids, liquids, and gases with temperature has been quite interesting because it has many applications. Thermal diffusivity is another interesting topic that we need to discuss. So we know about specific heat capacity per unit mass, heat capacity, and thermal diffusivity represents how fast the heat diffuses through a material. That is given by the ratio of the heat conduction by the heat storage. A material that has a high thermal conductivity or a low heat capacity will obviously have a large thermal diffusivity. A larger thermal diffusivity will actually give a faster propagation of heat into the medium. So basically, for a faster diffusion, it is desirable to have a higher thermal conductivity and a lower heat capacity. A small volume of thermal diffusivity means the heat is most absorbed by the material, and a small amount of heat is conducted further. Convection is another technique of heat transfer. The mode of energy transfer between a solid surface and adjacent liquid or gas that is in motion, and it involves the combination efforts of conduction and fluid motion. The faster the fluid motion, the greater the convection heat transfer. In the absence of any bulk fluid motion, the heat transfer between the solid surface and the adjacent fluid is by pure conduction. A forced convection is basically when you have a fan or a pump or wind that is actually forcing the convection. Whereas the natural convection is when the fluid is in motion caused by the buoyancy force that are induced by the density differences due to the variation of the temperature of the fluid. I'm afraid this is not in your course, so you don't need to know much about this. But definitely it's worth knowing the Newton law of cooling. And of course, we all know about Sir Isaac Newton, who is an English mathematician, physicist, astronomer. So further, we need to understand about radiation, which is basically, it deals with electromagnetic waves or photons. Then the Stefan Boltzmann law, which governs this mechanism, absorptivity, and the laws like the Kirchhoff's law. net radiation, heat transfer, how these things affect, and simultaneous heat transfer mechanisms while you are having radiation, conduction, convection all together, and how to solve problems, the software packages. Eventually, I think as an introduction, what we learned today is the thermodynamics and heat transfer, the application areas of heat transfer, historical backgrounds, modelings in engineering, specific heats of gases, liquids, and solid, energy transfer, something about first law of thermodynamics, the energy balance of a closed system for a fixed mass, energy balance for steady flow systems, surface energy balances, the heat transfer mechanisms also we got some introduction of, like the Fourier law of heat conduction, the thermal conductivity, the thermal diffusivity, some idea about convection, and we'll take up radiation in the next class. Thank you so much. Stay safe. See you soon.